Hey there, welcome back to Inside the Logic, real talk with FPGA engineers. Today we're cracking open the FPGA toolbox. What software and hardware do engineers rely on day to day? How do they test designs before they go live? What hidden tools make their lives easier? I am your host, Kevin Rosenquist. And of course, as always, I am joined by Charles Sobczak. Charles, how are you?
I'm doing good. How are you, Kevin?
I'm good. I'm good. Tell us a little bit about what you do over there.
Sure. I am the FPGA Workbench Manager, and so I run a small team here, and my area of expertise is signal processing research, and ASIC development, and FPGA development.
Awesome. Well, we don't just have one guest, we have two guests. Ryan Erickson is with us as well. Ryan, how are you?
I'm doing well. Thank you for having me.
Yeah, tell us a little bit about yourself.
Yeah, so I'm a senior FPGA hardware engineer here at Concurrent Real Time in Pompano Beach as well. My background is just FPGAs from the electrical engineering degree at UF, University of Florida. And what I do here is a lot of firmware design and FPGA design, creating algorithms and trying to create custom solutions for customers.
Awesome. All right. Well, I'm excited about today's topic. We're talking about some tools that you guys use. What's in the FPGA stack? So, you know, tell me a little bit about it. We got to, you mentioned simulated workbench in the past, FPGA workbench. Tell me a little bit about the tools you guys use.
Sure. So, FPGA Workbench is our main product suite that we have here for Concurrent Real Time FPGAs, where we use Intel Altera Cordis, which is an FPGA compiler and IDE designer. We use that under the hood in order for customers to be able to employ highly complicated FPGA designs with a higher level look on, with like a very simple GUI, almost like dragging and dropping blocks like an MS Paint. Very simple connections.
Wow,
It's
that's
you know
taking me back.
it's the idea is to simplify it as much as possible, and there's obviously complexities in there. There's obviously going to be similar to other products like MATLAB Simulink, where we're kind of doing these simulation tools with the drag and drop blocks and creating intelligent connections between these things. But we try to make the GUI as the graphical user interface as simple and straightforward as possible, because our goal is to lower the barrier to entry into FPGA design and allow for the customer to be able to take this highly powerful card and change the design and do these very quick prototypings and very, very quick bench testing, and allowing for the customer to change one signal from going to one pin to another. Maybe they want to do some math on it. Maybe they want to add some noise to the signal. And so we take advantage of we provide Intel FPGAs, and we take advantage of Intel's FPGA compiler. I think nowadays is Altera. It goes back and forth. Altera was purchased by Intel, and then Intel, I think, spun off Altera again. It's a whole back and forth thing, but it's the same product. It's Intel Cordis or Intel Altera Cordis, where is the program that they use for programming and designing FPGA designs to go onto their suite of FPGAs. So our cards are based on Intel FPGAs, and they have Intel FPGAs on them. And so in order for our customers to have our FPGA Workbench, which is an extrapolated version of that design flow, we have to take advantage of the actual real design compiler in between. And so importantly in our stack is we use the Intel Cordis IDE and compiler, not only for our own prototyping designs, but also to be built into customers whenever they're using our product. And so on a day-to-day basis, we as FPGA engineers are typically using Cordis all day, every day. And then as for the products that we have inside the building, we are all running on our Red Hawk Linux operating system. We are all using FPGA Workbench for not only testing the product to make it better for customers, as well as doing our own designs. It's honestly gotten to the point in its life cycle of where it is efficient enough to do these prototype bench testing that we want, that even as a developer, I use it to test itself all the time, which is, it's kind of interesting in the idea of like you have a fully fledged car to the point where you can go drive test the car when you make a change on it. And so so on a day-to-day, I'm using Intel Cordis for like deep coding, but if I'm doing some sort of hardware testing or anything, I'm using our products in-house. And I mentioned in a previous episode, Simulation Workbench is extremely helpful for communicating efficiently with the FPGA cards within the systems. And so if we're doing testing or development work or customer integration or anything, even if the customer isn't purchasing any or all of our software products, implementing Red Hawk Linux, FPGA Workbench, as well as Simulation Workbench and our other tools to combine them together for our own edification and testing has become very, very common and very commonplace in our testing process, because they're so well meshed together that it is almost a disservice as an engineer to not test it using all of the pieces, because even if the customer doesn't want all the pieces, making sure that it all runs together well is nice in case that they want to ever upgrade it in the future or change their current solution to include any new pieces.
Do you guys have a favorite tool? Is there something that you like best? Charles, maybe I'll start with you on this one.
So I do. So this is a little bit. So in terms of if we went under the hood and said, how does an FPGA engineer on our team operate? The flow starts with a tool called MATLAB, which is where you develop the algorithm initially. So this is kind of getting a segue into that flow. So MATLAB helps you develop the algorithm in floating point, and then you got to convert that floating point algorithm into fixed point, which is this tool called Verilog that we've talked about, Verilog or VHDL. So it's taking it from that floating point domain and fixed point domain, and then the next step is taking that Verilog and then putting it on the FPGA. So traditionally, I come a little bit more from the research side. So from the development flow of an FPGA engineer, I've always loved MATLAB, because and then MATLAB is sort of in the flow of customers who want to develop their own IP modules on our FPGA as well. But obviously, I love our product, FPGA Workbench. It is a very powerful product.
Yeah.
But in my career, MATLAB has been really very, very vital and important. And I think kind of like as Ryan was speaking about, we've gotten FPGA Workbench to a point now where if a customer wants to do something mathematical where it has waveform generation and multiplications and the standardized math, it can be done very easily just in the canvas. So you can have a person that literally knows nothing about an FPGA or Verilog or how to synthesize code or how to deal with timing, and they can put these blocks down in the canvas, connect them up, and in a matter of 30 minutes have a design where you're bench testing it. So that I think it's kind of it's beautiful that you can go from an idea to be testing it on your bench and seeing signals in an hour. That's really powerful. So
Yeah.
if I was going to say two tools, I mean, I love MATLAB, but then I think our tool is just very powerful, and it's improving and evolving over time.
How about you, Ryan?
Honestly, to build off Charles's last point, I wanted to mention a quick story where very recently we had a coworker. We needed to test something, and he had brought up to a couple of us, not specifically the FPGA team, like, hey, I need a card that creates this signal. It was a certain kind of square wave type-esque shaped signal, and we didn't have anything in the building that created that kind of signal. And I thought about it for a little bit. I was like, wait, I can definitely create that on our FPGA with FPGA Workbench, where if I take these 3 waves and add them together in a certain way, I can get exactly the signal that he wanted. And it was really cool because I got to kind of show off a little bit internally, but also it was kind of cool to see something that we've been theorizing for a long time, which is like, well, if a customer wants to do something, they just can. And in this case, I was the customer. I just could do it. And it was just like, it was cool to see, like, wow, we put together this thing and we say that it can create whatever you want it to create. And you can only come up with so many edge cases and test cases for your own testing ability before we make a release. I hadn't come up with this specific signal that they wanted to test in this edge case that they wanted to test. And I got to see like the whole process of an engineer needs something. We have a product that can just make it. And in the same day, we were doing the test that they wanted to run with that exact signal. And this could have taken weeks to find a specific part that made the signal if we weren't using some form of programmable card like the FPGA. So I'm very partial to FPGA Workbench. I love it. It's been the only project I've worked on since coming out of college. It is my main thing, but I'm also going to be honest. I love Quartus, which is, it's nice that we have it here. There was all of my training inside of university was specifically with Quartus. Most of the work I've done has been with Quartus. I like it. It's I like Intel Altera as a company. I like the work they've done with this. There's a lot of cool features in it. And so from a kind of what Charles was talking about, under the hood, Cordis, if I had to pick something under the hood, it would be Cordis. If I had to pick something, it's the whole hood. I want FPGA Workbench. That's my favorite.
Don't get greedy, Ryan. So do these tools, do they integrate with other systems? Does everything talk to each other really well from top to bottom?
Yeah. So a lot of our internal stuff obviously talks very well with each other. You know, we have our Red Hawk Linux operating system, and almost everything that we design in-house is based around that. And so we have this operating system as a baseline, and all of the programs and software that we create are made to run and run efficiently on that operating system. The beauty of that operating system is it's got built around hard real time. You know, if it says that this is taking exactly 7.37 seconds, it's taking exactly 7.37 seconds. Mm-hmm. It's really good for mission critical real time applications that can't take longer or shorter than the amount of time defined. And so a lot of what we do is built around that. And because of the kind of the foundation that we build off of in this real time operating system, all of our softwares and our drivers and our hardwares really communicate well together. And so in the case of the FPGA card and FPGA Workbench, we use these drivers that have been designed specifically for our cards to unlock the powers of real time and making sure that the cards are communicating efficiently with the system or any other computer, or directly with Simulation Workbench that is being controlled by the computer. It's all it seems like every permutation of one communication to another can be handled inside the whole suite. It seems that everything communicates well together and it's clean. But the beauty of it is, as recently this year, we have released new drivers that allow for everything I just described to be on other operating systems as well, and directly on all Linux, but not just Red Hawk Linux inside of our inside the house. So it's like we have Ubuntu and Red Hat Linux where we can directly implement these cards and communicate just as efficiently in similar ideas and ways on other systems without necessarily having the complete suite of what we have here. And all of the software that's built into FPGA Workbench and all of the software that's built into Sim Workbench very commonly will interact with each other, such as the software development toolkit that we have inside of FPGA Workbench is actually also put inside Sim Workbench so that a customer doesn't necessarily need FPGA Workbench to be able to communicate with the card. Now, they can't do their own designs on the card from Sim Workbench, but if they're just communicating with the card, there are lots of ways where we have redundant aspects of the software to where it's in one side and the other, so that we necessarily, if a customer only wants a certain functionality, they don't have to overbloat their system with different things that they don't necessarily need.
Mm-hmm. You know, I've had times in my personal life and in my career where I discover a tool or a program or something, and I'm like, where was this a year ago? Where was this 5 years ago? I wish I would have had that. Is there anything that you guys have access to now or use now that you were just like, that you had that feeling like, oh man, I wish I would have known about this a long time ago?
Yeah. So specifically for some internal operations and for speeding up both customer prototyping and our own testing, there is a method to where we can now, and it's a script that we have built into FPGA Workbench, that will effectively create a Sim Workbench project for you. Now, Sim Workbench projects are very complicated and they're very in-depth, and there's lots of bells and whistles that you can pick from. And that's nice. It's great. I love that. The issue is whenever you need to quickly make a project and you need it going immediately. And it's like, you know, if you need to get in a car and drive, you don't care what color it is. You just need to make sure that it's driving. If you have to spend time picking the color, you know, that can really kill time. And so we have developed this software process that allows reading the FPGA Workbench design that's on the FPGA card and efficiently creating pretty much the optimal test in Sim Workbench to be able to run simulations almost instantaneously. Just like, hey, here's your FPGA design. We see what's on it. I'm going to programmatically create this test to where you can pretty much immediately click a play button and it's up and running. Now, truth be told, that was created just when I got here. So I only hear people's complaints about how bad, like how nice it is to have that and how bad it was to create every project from scratch beforehand. So I can't say I had the feeling of where was this 5 years ago, because I wasn't here 5 years ago, but I can really see how much it speeds up process, because I've had to do projects by hand, and it not that it's bad to have all these bells and whistles, but when you're only testing one thing, you don't need 110 different options to pick from. So it's nice to be able to create these projects instantaneously.
Yeah, you're glad you have it, if nothing else.
Oh, absolutely.
Yeah. Charles, how about you?
Yeah, so I think that, in terms of the tools, we're all well integrated between the operating systems and simulation workbench and the hardware, but we're always sort of trying to sort of optimize that and remove sort of inefficiencies. And that's one kind of good example where we developed some automated code that removed a manual process. But yeah, so I mean, it's definitely something that's kind of always ongoing. Now for FPGA Workbench, we have some bigger ideas coming in the future where we'd like to reduce additional barriers to entry, where everybody now is using LLMs to develop code.
Mm-hmm.
And so we're coming up with a mechanism, as Verilog and VHDL, the code to program an FPGA are challenging. We're coming up with ways to potentially integrate some of those tools into FPGA Workbench in the future, which would additionally kind of lower the barrier to entry, where anybody who has any knowledge of programming can possibly develop some Verilog code. So there's things that are kind of on our roadmap. But yeah, that's always a goal of ours, is to try and make the blocks more synergized together, I guess.
I took a Fortran class in college. Am I ready to go on this then?
Yes.
That,
wow.
Oh, yeah.
Did you really? That's impressive.
Fortran and C.
Okay.
Yeah, I don't.
I took Fortran too. I think I took it the last year that they actually had it, and then they stopped.
I don't think it was really popular after that. So
C can be really helpful, because at FPGA Workbench we allow simulating a entire microprocessor inside of the FPGA card, because since FPGAs involve all of the different types of building blocks of computer architecture, we have allowed the customer to take advantage of a pre-existing Intel design where you can create a computer inside of your FPGA. And I'm not exaggerating. It's a full computer inside of the FPGA. And, it's not a big computer, but it can run C code that you create and C programs that you create directly on the FPGA. And so we have created a suite in FPGA Workbench where you can take the C code in software, compile it, and then burn it onto the computer that's existing inside of the FPGA.
Impressive.
It's pretty cool. It's kind of almost like Inception kind of thing. There's layers to it. It's like you got a computer that has an FPGA card inside of it that has a computer inside.
It has a computer.
But if you need a computer running calculations, or a CPU doing some form of, maybe you're dividing something, or you need to run like a state machine, or you want a program running, but you don't want to commit the CPU on your host computer to doing that program and constantly communicating with the FPGA doing that. It is worlds of help to have that real program, and it's a real computer program embedded into the FPGA. And so to answer your question, the C code will help 100%.
All right. Well, yeah. Not that I could refer to any of that. It's been a minute. So, but hey, at least I did it. All right. Well, thanks for joining us today on Inside the Logic, real talk with FPGA engineers, Charles Sobczak, Ryan Erickson. Thank you guys so much for joining me today. Really appreciate it.
Yeah. Thank you so much.
Yeah. Thank you, Kevin.